Hello and welcome to the fourth video of the P2 chapter, Sequences and Series. On the screen is a starter exam question to review geometric sequences. Pause the video now if you've got time to give this a go, and then I'll go through the answers. So we've got the third term of a geometric sequence is 324, and the sixth term is 96. If we remember, we know what the general term of a geometric sequence is AR to the n minus 1, then I can write this as the third term, which is AR 3 minus 1 is 2. They're telling us is equal to 324. And the sixth term, which is AR to the 6 minus 1, 5, is equal to 96. So that's the information we start with. Part A. Show that the common ratio of the sequence is 2/3. Okay, well, we've done this a few times before now. We take this equation divided by this equation, and we can cancel the A. And in this case, that gives us 96 divided by 324. So our A's cancel. We've got r cubed is equal to 96 over 324 is 8 over 27. So r is equal to the cube root of that, which is 2 over 3, as required. Part B, find the first term of the sequence, which is A, and now we know r is this. We can use that in here to find A. As with some exam questions, this one, even if you couldn't do all of this, if you got one of these equations from the information, you can use the fact that you know from the question here that r is 2/3 to find A. So even if you didn't get both marks here, you potentially could still get both marks here. So we've got AR squared is equal to 324, and we know now that r is 2/3, or we know from the question, either way. 2/3 squared is equal to 324, and if you put that on your calculator, we get A is equal to 729. Part C, find the sum of the first 15 terms. So here we've got n is equal to 15 using our sum formula for geometric sequences, a 1 minus r to the n divided by 1 minus r, or the other way around if you prefer the other option. And we know all of these now, so S15 is 729 times 1 minus 2/3 to the power of 15, all divided by 1 minus 2/3. And I have that on my calculator already. The answer there is 2182.005639. I wouldn't normally give that many decimal places, but I think that that is exact because it doesn't fill my calculator screen. So I'm going to leave it like that. It doesn't specify to round it to the nearest whole number or anything, so I think I'm okay doing that. Final part, sum to infinity. Now we can do this because we know the common ratio is less than 1. So we can find the sum to infinity of this sequence. Remind ourselves the sum to infinity is a over 1 minus r. So here that is 729 divided by 1 minus 2/3. And 729 over 1 minus 2/3 is 2187. And you can see that this number here is getting fairly close to that, even by the time we get to just 15 terms. So that's an exam question on geometric sequences. In this video, we're going to look at a bit of notation. There's no new maths as such, but how to use this notation is important because it's often used in exams and in real life situations. So using what is called sigma notation. To explain why this is useful, we're going to do this question first. What is the sum of the first 5 terms of the arithmetic sequence given by the rth term, ur is equal to 2r minus 3. Now don't let this confuse you. The rth term is just another way of saying the nth term. There's a reason we use r and n. I'll come back to that in a few minutes. But let's talk about how we would normally do this. The first 5 terms. Well, in this case, probably we would just work out what they are. Oops. Go into red. So u1, when r is 1, 2 times 1 minus 3 is minus 1. Second term, when r is 2, 2 times 2 minus 3 is 1. When r is 3, that's a 3, and you can see the arithmetic pattern appearing. It's a common difference of plus 2. So that must be a 5, and this one will be a 7. Now that we've got that, there are 2 ways we can solve the question. The sum of the first 5 terms. Well, because I've got the first 5 terms and it's only 5 of them, I could just say, well, let's just add them together. Minus 1 plus 3 plus 5 plus 7 is equal to 15. Or if there were more of these and I had the general pattern but I didn't want to do that calculation, I could use our normal way, which is the formula. So we've got n over 2 times 2a plus n minus 1 times d. And from these first 5 terms, we know the first term is minus 1, that's the a. And we know that the common difference, we can see by the time we've done 3 or 4 of these, the common difference is 2. And of course, the n is 5. We want 5 terms. So we could use this formula as normal by the time we have seen the pattern. 5 over 2, 2 times the first term minus 1, plus n minus 1, which is 4, 5 minus 1, 4, times the common difference, which we can see is 2. And that also will give you 15. Okay, so there's 2 different ways. Because we've been given the formula like this, you're probably going to want to figure out some of the terms. Once you've got the terms, if you've got all of them and you just want to add them, that's fine. But if you've got the pattern and you want to do the formula, then we can use this method. Strangely, what we're talking about today doesn't really change any of that. What we're talking about today is the notation of the question itself. Because writing all of this out, what is the sum of the first 5 terms of the arithmetic sequence given by the rth term this, can be all condensed using this thing here, which is the Greek capital letter sigma, and you can write that whole question with this. You're more likely to see it also with this word in front. Calculate this. So let me just explain where this is coming from. Turning this into a question, what is, that's the calculate bit. Work this thing out. What is it? What's the answer? The sum of, that's the sigma. Sigma here means the sum of. The first 5 terms, that's this number down here. It's saying start at term number 1 and keep going until you get to term number 5, including this one and including this one and including all the ones in between. Of the arithmetic sequence, well, you wouldn't necessarily know it was arithmetic until you'd started doing the terms, or if the question said it. But the sequence given by the rth term this in here. And if it said calculate and it showed you this, you would do probably exactly the same thing. Work out the first few terms, and then either work all of them out and add them together like this, or work enough of them out to get A and D, and then apply the formula. So there's no new maths as such. It's just understanding what this question means when you see this capital sigma. And I'll be honest, if I was to write it, I'd probably just write it like that. It wouldn't look like a real capital sigma that you would see on a computer. That's probably how I would write this question. And that's it. I'm just going to go through a few examples. There is one thing to be careful of on the third example. We'll come to that when we come to it. So if you're writing notes, quick summary, capital sigma, this thing, is used to show the sum of a series. The formula often has an r, but not always, and we write it in terms of the rth term, and the reason for that is so that we can still use n to represent the number of terms that we want to add together. That's why we have r and n. The number underneath is the first term to use in your sum, and the number at the top is the last term to use, inclusive. You want to include this one in your sum. Okay, our examples. Calculate the sum of this sequence from the first term to the 20th term. So to show you how I would do this, I would put r is equal to 1. So u1 is 4 times 1 is 4 plus 1 is 5. Then calculate the second term, when r is 2, 8 plus 1 is 9. And from experience, I know that this is going to be an arithmetic sequence. If you're not sure about that, just do a few more terms. Keep going until you're clear it's arithmetic or geometric. So 3 would be 13, u4, 16, 17. So you can see from these four, we've got an arithmetic sequence. Important part, a is 5 and d is positive 4. From the question, I want to start at the first term and go up to the 20th term. So n, I want 20 terms, the first 20 terms. And then to do the sum, I can now go to the usual formula. And for arithmetic sequences, that is n over 2, 2a plus n minus 1 times d. And I know all of those things. So 20 over 2 times 2 times 5 plus n minus 1 is 19 times 4. Put that on my calculator, 2 times 5 plus 19 times 4, times that by 20 over 2 is 860. So the sum from 1 to 20 of 4r plus 1 is equal to 860. Second example. This one looks a little bit different, but it is not. Here, what I'm trying to emphasize is that you can use any letter here. R is quite common, but it's not the only letter that will get used. So if it says K or X or Z or anything, don't let that throw you. What we're going to do, I can see that this from the general format of the term here, this is a geometric sequence. Because if you remember, our general term is ar to the n minus 1, and that matches. So I can actually say straight away, a is going to be 5, r is going to be 3. And I want from the first term to the 12th term, so n is going to be 12. And I'm using a geometric sequence, so the sum of a geometric sequence is a r to the n minus 1 over r minus 1. And you can see I've automatically gone back to this format because my r is greater than 1. So I've got 5, 3 to the power of 12 minus 1 over 3 minus 1. And I guess if you wanted, you could change the Sn notation there to the sigma. Yeah, you can see my sigmas are not very good. And if I put that on my calculator, 5, 3 to the power 12 minus 1 divided by 3 minus 1 is 1,328,600. quite a big number. Okay, our third example is a little bit different. I'll pause here just for a second to see if you can have a look and understand why it's different. Because on the surface it looks identical to what we just did. So obviously geometric, A is still 5, R is still 3, I still want up to 12 terms, but down here you can see I don't want to start with the first term. I want to start my summation from the 5th term up to the 12th term, including the 5th term, including the 12th term, all of the terms in between, but not the first 4 terms. How do I do this? Well, the answer is that I can do this in 2 parts, because if I choose to add all of the terms together from 1 until 12, then add all the terms from 1 until 4, I can subtract the ones I don't want. So I'm going to show you that by writing this using the same notation. I'm going to do from the first term to the 12th term of this sequence, and then I'm going to subtract a whole other summation from the first term to the 4th term of this same sequence. Now here's a common mistake. A lot of my students, if they're going to make a mistake, they end up putting this number here. But we want the 5 included in the sum, and this will include this number in this sum. So I want from 1 to 12 first, and then the ones I don't want, numbers 1 to 4. So it will always be 1 less than this number here, so that this is still included in the answer that I get. Okay, following it through. From 1 to 12, I'm going to need to... Oops, that was the general form of what we're going to talk about in a second. So I still know that A is 5, R is 3, and for this first one, N is 12. Over here, A is still 5, R is still 3 because it's the same sequence, but for this sum I'm using just the first 4 terms. So putting this into our formula, we've got Sn is equal to A r to the n minus 1 over r minus 1. So we've got 5, 3 to the 12 minus 1 over 3 minus 1. Now I'm just going to put the answer there because we had that from our previous question. That was 1,328,600. And then from there we want to subtract almost the same thing, but the first 4 terms. And that is 200. So we've got 1,328,400. And if you think, wait a minute, that number's very different, it is because this is a geometric sequence. So although the numbers start quite low, they get high very quickly, and once you get past term 4, they get higher even quicker, and as you get past term 10, they get much higher, much quicker. So the further down the sequence you go, the higher the numbers get. So you would expect the first few to be much smaller than the next sort of 8 or 9. So there we have it. This is an example of this general rule here. You can always split a summation if you don't want to start with the first term. You kind of have to start with the first term and then subtract from the first term up to the terms that you don't want. With the common mistake being that people forget to take this down 1 up here. So be careful of that. And that's it. So other than this rule here, there's not a lot of new maths in this video. It's all about the notation. So if you want to practice that notation and you've got the Pearson EdXL textbook, you can use questions from exercise 5F. and maybe I'll see you in the next video.